Okay, so now we have Soumyajit talking about nearly tight bounds on approximate equilibria.
So thank you everyone for coming, and this is a joint work with Professor Mumbai. So let's start. Okay, so think about this, that some voters are distributed according to a bounded density function. So what do you mean by bounded? Bounded means that for any x in this interval 0, so the distribution is defined in this interval 0, and it's bounded by some constant n. And this is the distribution of voters.
It need not be bounded from below.
So it's a density. So let's think about that. It's greater than equal to 0.
No, like can it be double exponentially small?
This m can be anything you choose. It's a constant.
Yeah, it can be bounded anything.
Yeah.
Below 0, double exponentially.
So yeah. So and then the candidates are choosing their position over this 0, 1 interval like this. Blue candidate and the red candidate and blue candidate, and this is the midpoint. And the voters vote for the closest candidate. So what does it mean? It means that the voters in this red region vote for the red candidate, and the voters in this blue region vote for the blue candidate. And strategy profile is equilibrium if no candidate can strictly increase its vote by moving to a different location. So what does it mean? So just focus on the red candidate. Just think that the red candidate is moving towards the blue candidate. Then this midpoint will also move towards the blue candidate like this. That means that the red candidate can strictly increase its vote like this from here to here. So then this is not an equilibrium, right? Because the red candidate can increase its vote. And
So lots of things are the same. One is about the voters.
So the voters are the distribution. That's it. I mean,
One is the candidate, other is the voter.
yes.
So candidates are distributed according to the density.
No. The candidates are this small dots.
Candidates can choose
Arbitrary position. They know everything. Yes, they know everything. And there is a small assumption in our model, that is, so the minimum distance between any two candidates should be greater than equal to delta. So yeah, so for all I not equal to j, the distance between two candidates should be greater than equal to delta. Okay. So we have only two parameters right now. We know that is the the capital M and the delta. So yeah, so then what is an equilibrium for two candidates? So it turns out that for two candidates, we always have an equilibrium like this. So let's say this mu is the median of this function. And if you place the candidates like this, then it's an equilibrium, because if someone moves, it cannot get more than half, and it's getting approximately half. So for two candidates, there is always an equilibrium. What about three candidates? So now you have like three candidates. Now, as the example of the second slide, the red and the green candidate or the olive candidate will try to go as close as possible to this blue candidate and can strictly increase its vote. And it turns out that for three candidates, you can prove that there is never an equilibrium. Take any distribution, will not get any equilibrium. So if there is no equilibrium, let's talk about approximate equilibrium. So let's say the voters are distributed with this nice piecewise linear function, and these numbers are the mass, the area under the curve. And this is a 1/8 additive approximate equilibrium. What does it mean? It means that focus on any candidate. So let's say this red candidate. This red candidate can go to x2 minus delta, but it cannot get more than this 1/8.
It can't be the previous thing. You're saying for any distribution, there is no equilibrium, or there is a distribution?
No, there is, for three candidates, you take any distribution, there is no equilibrium. Now I'm talking about.
What if it's a point mass? So the bounded by m.
Yeah. The function is bounded by m. So there cannot be a point mass kind of thing. It's a density function. Yeah. So yeah, so it's a 1/8 additive approximate equilibrium, because to take any candidate and if you move it, it cannot gain more than 1/8 votes. So formally, strategy profile is a epsilon additive equilibrium if no candidate can increase its vote by epsilon by deviating to another location. And the question we want to ask is that given a distribution and m candidates, what is the best epsilon we can achieve? That's the question we want to talk about. So why approximate equilibrium? So Ritter and Lipsy showed that in this model, generally we don't have a Nash equilibrium. Okay? But this non-existence of Nash equilibrium does not say anything. I mean, if you can go close to a equilibrium, that we don't know by the non-existence of an equilibrium. But approximate equilibria can give you this insight that how stable the model is. And also in practical applications, we also use approximate equilibria because this pure Nash equilibria is hard to find or may not exist. Okay. So these are the notations. So just I'll just keep it and I'll just say it through a picture. So let's say there are three candidates and these dotted lines are the midpoints of them. So the left utility of a candidate is that how much vote it gets from left. So like the second candidate is getting this much vote from the left and it is denoted by U2L. Similarly, the first candidate is getting this much vote from the right and it is being denoted by U1R. Okay, that's what I have written in the last notations by integration and all. But yeah, this is what it is. So yeah, so for three candidates, we know that epsilon is strictly greater than 0 because there is no equilibrium, right? So the question is that then what is the lower bound? So the question we want to ask, what is the best epsilon you can achieve for three candidates? And it turns out that we proved that 1/12 is the best you can do. You can't do better than this. And this is a surprising thing because that means that if you have an election like this or something, like there are three candidates, then there is always a candidate that can increase its vote by 8.5% to, I mean, after deviating to a location. So we'll prove this lower bound in the next slide. So let's prove it. So let's say we have a strategy profile like this. So these are the location of the candidates and it's an epsilon equilibrium. Then the first claim says that you focus on the second candidate and then I'm saying that the left utility and the right utility are bounded by epsilon plus m delta. So pictorially it's saying that if this is the second candidate, then it cannot be more than epsilon plus m delta. So how do you prove this? So we'll prove it by contradiction. Suppose that the left utility is bigger than epsilon plus m delta. And now suppose the first candidate deviates to x2 minus delta. So previously the first candidate was here and now the first candidate is deviating to this location x2 minus delta. Now notice that in this interval the whole mass is more than u1x plus epsilon plus m delta because I mean the left utility of the the second candidate was more than epsilon plus m delta and u1x is the utility of the first candidate. Okay? And also by the property of the function, this mass is bounded by m delta because the function was upper bounded by m and this interval is delta. So then the first candidate is getting after deviation, the first candidate is getting more than its utility plus epsilon, which is a contradiction because we assume that it was an epsilon equilibrium, but the first candidate can get more than epsilon. So it's not an equilibrium. So contradiction. So the claim 1 is done. Now, yeah. So now the claim 2. So claim 2 says that the left utility of the first candidate and the right utility of the last candidate is at most 3 into epsilon plus m delta. This is the same. I mean, this proof is exactly same like the last claim. Suppose that it's more than this quantity. And so from the claim 1, we know that the player 2 is getting at most 2 epsilon, right? So yeah, so the player 2 is getting at most 2 epsilon plus m delta. Then then you can show that if the second candidate goes, deviates to x1 minus delta, then it can get more than epsilon, like this picture. So this is bounded by m delta, then it's getting more than epsilon. So it's also a contradiction. So what we have this. So we have an upper bound on this interval, we have an upper bound on this interval, but we don't have an upper bound on this and this part. The thing is that we'll tackle it in a different way. We'll find a bound on this whole interval, this x1 to x3, and that's what the claim 3 says. So pictorially, the claim 3 says this so the midpoint of x1 and x3 is this. Then this mass is upper bounded by 3 into this, and the proof is exactly same like the claim 2. That if it is more than that, then the second candidate can gain more than epsilon. So, so what we have like 3, 6, and 3, which is basically 12. And yeah, you will get epsilon is greater than equal to 1 by 12 minus m delta. And delta we can take arbitrarily small. So if you take delta tends to 0, it becomes 1 by 12. So the lower bound is 1 by 12, right? Then what about the upper bound? And it seems we have a result that there exists a distribution where you can achieve 1 by 12. And this is the distribution, and I don't want to say about the distribution. It just looks like this, and you can show that this configuration is a 1 by 12 approximate equilibria, and this is tight. So this 1 by 12 bound is tight. So the question was, what was the base epsilon for 3 candidates, and it turns out to be 1 by 12. So we can't do better than this. So now the question we want to ask. So let's say I give you a distribution. And I ask, what's the best epsilon you can achieve for 3 candidates? How much you can achieve for 3 candidates? And it turns out that 1 by 6 we can always achieve. So given a distribution, you can always achieve a 1 by 6 approximate equilibrium with three candidates. And this Cartan-Eval queries are like, we have a distribution and we have to somehow use the use the distribution. So how we use the distribution with this Cartan-Eval query. So it is very known queries in cake cutting protocols. So yeah, I just then skip this, and we also have a lower bound. So this lower bound is, so let's say I ask you a question that what is the worst case distribution for 3 candidates? And it turns out to be 1 by 6. There exists a distribution where you cannot do better than 1 by 6 approximate equilibrium. So then these two are also tight.
You cannot do better than 1 by 6 approximation in any amount of time, even in exponential amount.
There do not exist any equilibria better than this 1 by 6. And this is a general result that I'll show. So for m candidates, but yeah, this is the thing. So now what we can say about m candidates. So m candidates, if I give you a distribution, it turns out that we can always achieve a 1 by n plus 1 approximate equilibrium.
So when you say algorithm, what's your input? What is the...
So the input is the number of candidates, and you can ask this queries. So this Cartan-Eval queries are like this. So this eval query is that I give you 2 points, and you'll answer that how much mass between these 2 points. And this cart is like, I give you a point and a mass. You tell me the closest point or some tie breaking that this is the point where you have this exact mass between these 2 points.
And the computational cost of such a query will depend on what the...
So we don't, so the algorithms.
One query.
Yeah, exactly. Okay. Yeah. And for m candidates, it turns out that you can always achieve a 1 by m plus 1 approximate equilibria. And the algorithm is very simple. You just put the candidates on the m plus 1 at pointers. Okay. Now, for the 3 candidate, we asked this question that what is the best epsilon you can achieve? But if we ask it for more than 3 candidates, it's actually 0, because Pyne and Lipsy showed that for uniform distribution and more than 3 candidates, you will always have there always exists an equilibrium. Okay. So what question we can ask for this for m candidate? So we can ask then what is the worst case distribution? And it turns out that you can't do better than 1 by m plus 3 approximate equilibrium. And the proof I will show in the next slide. So there exists a distribution where cannot achieve more than, I mean, a better than 1 by n plus 3 approximate equilibria. So yeah. So this is a lemma. So this lemma, so you think it like a function that, so I give you three parameters, this A, gamma, and L. And this lemma is saying that there always exists a function which is integrable and bounded with these properties. The first property is that in this interval 0 to L, the function has a mass of exactly A. And this is not very interesting. This you can achieve. The interesting part is this property. So you take any y in this interval, then the integration from y by 2 to y is bounded by some constant gamma. And how do you achieve this function? So this is the thing. So the function is saying that this is the interval 0, L. You pick a y. So it says that this mass is bounded by gamma. You pick another y. Then also this this mass is bounded by some gamma. So how do you know that this function exists? So let's go through some intuition. The intuition is this. So you integrate the 1 by z from y by 2 to y, and it's log 2. That means the integration does not depend on y. It's some constant log 2. But this 1 by z is not bounded, we know that. So you have to truncate, you have to scale, and this function will give you the guarantee that if you take any y, then y by 2 to y is bounded by gamma in this integration. So if you take A and L, if you take A and L equal to 1, then it's just a density function, right? And we'll use this function here in our lower bound. So take A and L equal to 1 and take this function. So suppose this is an equilibrium, an epsilon equilibrium. Then by the property of the function, to take any candidate other than the first candidate, then the left utility will always be bounded by gamma. And the proof is just one line. So the left utility of any candidate can be written like this. Just forget about the notations and all. And then you can just, so this is a trivial inequality. You just change the x, you just forget about the xk minus 1. And if you think xk as y, then it's the property of the function. Okay. So the left utility of any candidate other than the first candidate is bounded by gamma, upper bounded by gamma. And the next lemma is saying the right utility you can also bound by epsilon plus gamma plus m delta. So basically the picture is this. So focus on this candidate xk plus 1. The left utility is bounded by gamma from the last claim. And this claim is saying that the right utility is also bounded by epsilon plus gamma plus m delta. How do you prove that? So it's so this is the intuition of the function. So the function has this property. So this is xk plus 1, and we know that this is bounded by gamma. Okay, I mean this utility is bounded. The left utility of the xk plus 2 is bounded by gamma. And if you move the candidate a little bit left, then also it is bounded by gamma because of the property of the function. Okay. So now think about this. So same idea. Let's say by contradiction, the right utility of the kth candidate is more than epsilon plus gamma plus delta, and you move the k plus 1th candidate to the close, xk plus delta. So the picture looks like this. Now you have this bounds. So from the functional property, this area is bounded by m delta. Actually, m delta by 2, but let's say it's bounded by m delta, and also this is bounded by gamma. So then, how much vote this xk plus 1 candidate can lose? That is gamma plus m delta. So how much it's gaining? It's gaining more than epsilon, because gamma and delta it can lose at most. Then as the right utility of the kth candidate was strictly more than this, then the k plus 1th candidate can gain more than epsilon. Okay, then it's a contradiction, because we assume that it was a epsilon equilibrium, right? So the picture now looks like this. Okay. So now focus on the k plus 1th candidate. So k plus 1th so now you have a upper bound on the utility of these candidates, intermediate candidates, which is gamma plus epsilon plus gamma plus m delta, which is epsilon plus 2 gamma plus m delta. And as soon as you have a utility bound on this intermediate candidate, you can also bound the left utility of the first candidate and the right utility of the last candidate. Sorry, it will be M, the last candidate, and which is 2 epsilon plus 2 gamma plus 2 m delta, and the proof is exactly same. I mean, if some intermediate candidate deviates to any of these locations, they can get more than epsilon, the same proof. So the picture now looks like this. Now tell me how many intervals are there, like this, xk plus 1, xk plus 1, x plus 2, that is m minus 1, because there are m candidates. And each interval is bounded by epsilon plus 2 gamma plus m delta. So then you have this, and we have proved that the extreme left and the extreme right mass is also bounded by this 4 into epsilon plus gamma plus m delta. So now just forget about this gamma and delta and focus on the coefficient of epsilon, that is m minus 1 and 4. You add them, you get m plus 3. Okay. So we'll get a lower bound of m plus 3. And yeah, so if you put m equal to 3, you will get the 1/6 bound for three candidates. Okay. Now, how much time I have? 10 minutes? 10 minutes. Okay. So it was for a density function. Now Raghu asked that if there are point masses, then what can we say? So is this bounds holds? Okay. So now let's talk about the point masses. So now let's say there the voters are the points here. So here there are 6 equidistant voters. And the candidates are choosing location arbitrarily on this 0,1 interval. So now tell me what is the utility of this candidate, the first red candidate. It's 3, 1, 2, 3. And also this candidate is getting 1, 2, 3, and it's an equilibrium. You can see, I mean, whoever moves cannot get more than 3. And in the point masses case, actually, there can be equilibrium with 3 candidates also. Previously, in the density case, we didn't have an equilibrium for 3 candidates, but in this point mass case, you can have an equilibrium. Okay. So formally, there are n voters, n candidates, and n voters are choosing locations like this, P1, P2, Pn. And note that, I mean, they can be equal also. I mean, all of them can be equal. That means that in one position, there are n voters. Candidates are exactly, so candidates have the exactly similar nature as the continuous thing, I mean, the density thing. So the candidates are choosing distinct positions, and the voters vote for the closest candidate, the same thing. But here, there can be 2 candidates closest to 1 voter. In that case, if there are multiple closest candidate, then the voter just divides its vote equally. And how do you define an approximate equilibrium? Same, the equilibrium, I mean, profile is a epsilon approximate equilibrium. No candidate can increase its vote share by epsilon n here, because in the density case, the mass was normalized to 1, but here we have n voters, so there is a n. That's the only change. So it turns out that the same upper bound holds. There is an algorithm. The algorithm is very similar to the algorithm used in density, and you can achieve a 1/m+1 bound. Also, there exists a voter distribution where you cannot achieve better than 1/m+3. So this I'll just prove. It's I mean, I'll just give an intuition that what distribution you should take. So recall the previous distribution. The previous distribution had a property that this left utility is bounded by gamma, and if we move this candidate to some left, then also it is bounded by gamma. So how can this be replicated in a discrete value? I mean, now we have point masses, but we want this kind of property that if we move this candidate, still the number of votes are bounded by some constant. The idea is this. Suppose the first voter is at 0.0 and all the other voters are points like this. So the first voter is on 0.0, the second voter is at 1, the third voter is at 3, the fourth voter is at the position 3 into 2 plus 1, that is 7. So it's an exponential blow up. But there is no problem because we want to show a lower bound, not some algorithm. And if you take that, now see this. So let's say this is a candidate xk and this is another candidate xk plus 1, and this is some voter's location pi. So see this, the midpoint between xk and xk plus 1 should be greater than pi minus 1, because pi by 2 is itself bigger than pi I minus 1. Then the midpoint is also greater than pi minus 1. And in this case, if you move this candidate to a left, then also it is greater than pi minus 1. So this distribution has the same property we had, like the left. I mean, if you move this candidate left, then also, I mean, the left utility of this candidate is bounded by 1. So there it was gamma, it is 1. So if you use this, you will get the bound. This, I mean, after this, you will have to do some counting argument and you will get the same 1 by n plus 3 bound. So the open questions are like this. So we have an upper bound of 1 by n plus 1. We have a lower bound of n plus 3. Can you close this gap? We don't know. Okay. Maybe it's 1 by n plus 3. Maybe it's 1 by n plus 1. We don't know. So can we, and also can we extend this model to higher dimensions, also like graphs? So there are words like Pyne and others who has worked on graphical model. You have so the nodes are the points where the candidates can be, and the edges are the distribution, and in the edges there are a distribution of voters. So they have worked on that model, but this two-dimensional model, I mean, there can be some interesting questions, but yeah, so if anyone has any question.
The key candidate is there were two types of results, something where 1 by 12 was the type thing.
Yeah. That's what I said. So for 3 candidates, we know that there is no equilibrium, right? For any distribution. So the first question you should ask, then what is the best you can achieve? Because you know that epsilon cannot be 0. So if I give you a distribution, you know that the epsilon cannot be 0 there because there is no equilibrium.
Yeah, so there were two. I just got a bit. There were some results that something about 1 by 12 being
1 by 2 means don't give me a distribution for any distribution not to better than 1. And if I personally choose a distribution, you cannot do better than 1.
Okay.
Any other questions?
Hi. So you have this notion of polytime. So poly is what?
Yeah. So let's go to that slide actually. So this 1 by 6 you are asking. Yeah. So I mean, for this 1 by 6, so poly in this curtain eval queries, and there will be also an error because you have to do a binary search in an interval, and there will be some error, and that error will depend on the distribution.
Poly in the number of voters and
No, not the number of voters, because you don't. So poly in the number of candidates.
the number of queries you're going to make to this pattern.
Yes.
When you say poly error, it's called secant.
Huh?
Secant is 3, right? So here actually
No, for three candidates also there can be some error. I mean, you have to do a binary search with some property. That's it.
Poly in the
error.
Poly, huh?
So to get to epsilon error, you will poly in 1 error.
Yes. You have to do a binary search.
No, sorry. It's already
Huh? No, it's not that epsilon. I'm saying it's some other error. So I'm saying that. So let's say I give you a distribution like this.
So if pattern eval query comes with an error, and that's it.
So that's what I'm saying. So let's say. So let's say so you have like this. I mean a distribution, and I ask you to find a point, some x2 and some y point and some. Yeah. So no. So
So pattern eval queries are like that.
yeah, the pattern query results are exact, but this epsilon will have some error.
What is this?
This 1 by 6.
Oh, it will be 1 over 6 plus or minus.
Yeah.
So to get to 1 over 6, so it will be 1 over 6 plus epsilon.
Yes.
And you will poly 1 over epsilon.
Yes. So this epsilon, so you are doing this binary search now. So there will be log.
So it's poly log 1. That's what you will usually follow.
Yeah.
Poly log 1.
Yeah. Any other question?
Any more questions?
Yes.
For the 2 weeks, answers change drastically if I kind of wrap around.
Wrap around.
If I treat.
So yeah, so I don't know about that, but so this is called Hoteling's model, and so this paper by Eaton and Lipsy, they have actually worked on a circular market. So now the distribution is on a circle, and actually they have some results on that, but I actually don't recall that. But yeah, there are work on that. You can see that paper.
Any more questions? Okay, if not, then let's thank somebody.
So guys, there is food in if you don't know where that is, you can either follow the people who know or you can just smell and try.